The computer scientist I decided to go with was Donald Knuth, who had profound contributions to algorithm analysis and literate programming in the field of computer scientists. He's also very well known for his work on the art of computer programming, which is a pretty well known book on the foundations of computer science and all the different topics that encompass it. So to start off, in his early life, Donald was born in Milwaukee, Wisconsin. From at a young age, he received a scholarship in physics for the Case Institute of Technology, where he started working on the IBM 650 terminal, which was really where he got into writing computer programs and understanding like compilers and low-level parts of computers. So after Donald gained interest in working on the IBM 650, he basically mastered the manual of using it, and after understanding the compiler and writing programs and learning how to debug and all these foundational aspects of computer science, he realized that he could probably rewrite this compiler to be better than it actually was. So after doing all this and putting all this work into this IBM 650 computer, in 1960 he published two mathematics papers in the middle of working at or in the middle of going to school at Case Institute of Technology, and graduates within 2 years. He ended up working as a software consultant after that, and had written a 3,000-page book on compilers by this time, so quite a bit of work done. And then by 1966, he had written a 3,000-page book on compilers. And then by 1968, he had started on the first 3 volumes of The Art of Computer Programming, which were fundamental algorithms, semi-numerical algorithms, and sorting and searching, which, as we all know, are still a part of the CS curriculum today. And what this did was it gave people a baseline on how to analyze these algorithms in terms of like time and space complexity, and going. He also added on volumes that expanded on other topics like recursion and dynamic programming and all that kind of stuff that we're still taught. So in 1968, he started and continued this career for the rest of his life, actually, or up to the present day, I should say. He is still alive as a computer science professor at Stanford University. And throughout this time, he really built a legacy for himself, notably with 2 algorithm contributions that he made, or at least was part of creating, one of which being the Knuth-Bendix algorithm. And this algorithm is basically it's more catered towards the math side of computer science, and it's more applied in math concepts than it is CS, but it's still definitely very useful, especially when analyzing algorithms and creating formulas from those. And it basically allows you to reduce any algebraic structure into its simplified normal form, which allows you to see similarities or determine if 2 structures are the same. So say if you have 2 mathematical proofs, you can use this algorithm to completely reduce both to the normal form and say maybe the expanded form look different, but when you use the algorithm on both, you can see similarities or possibly see that they're the exact same proof. This was somewhat used in compilers, not really any modern ones, but still had an effect on computers and the computer science field. The other algorithm that he's famous for is the Knuth-Morris-Pratt algorithm. And this one was a string searching algorithm that is still used to this day, still very popular. And basically what this did was use a hashing function to iterate through a really long string to find instances of a smaller string subset within that. And this is still used to this day for DNA sequencing and bioinformatics, spell checkers, plagiarism detection, and music sequencing. So along with creating these algorithms, Knuth also put a lot more work into the art of computer programming, adding on, I want to say there was 12 volumes versus like the initial 4 or 5 that he had started. So not only adding on to these algorithm analysis volumes, but he also added stuff like data structures, advanced data structures, and intertwining these algorithms with these structures. Also a lot of stuff on compilers and like low-level theory stuff. With this, he also created his very own language, which was the Mix language, MIX. And this just gave people a way to easier visually understand how these low-level like assembly languages worked, which kind of shifts into his focus on literate programming. He made it well known that he vouched for the advancement of literate programming just because this type of programming made understanding code, writing code easier for the human mind because they're reading it and writing it in a sense that is closer to natural English rather than just random numbers and patterns that you would have to manually, or I guess, put more time into understanding. This relates to his invention of the text language, which is now transformed into the language LaTeX, or I guess it's probably just tech. But this is used in mathematical papers and technical documents, and this language was made to make it more visual, make mathematical concepts more visually easier to write and just more accessible for the average person. And by creating a language like this, you can have a pretty big effect on how easy it is to write these papers and display mathematical concepts and computer science concepts, which still has a very profound effect today. All right, and just to wrap this up towards the end here, some awards he received was the very first Grace Murray Hopper Award from the Association for Computing Machinery in 1971, the Turing Award in 1974, and the National Medal of Science in 1979, just for his broad completion of all these major contributions to computer science. And he just had his hands in so many different parts of the field that that's what most of these awards are recognizing. But his legacy and lasting contributions really just involve like vouching for literate programming and really pushing that, creating tech, which was converted into LaTeX, and vouching for literate programming and stuff like this. I think without people pushing for it, we probably wouldn't have these higher level languages like Python we see today, and even Java and all this, compared to what he was using back in the day, like Fortran and these low level assembly type languages. And on top of that, without a doubt, the art of computer programming revolutionized the way computer science was looked at as a whole and how it was taught, covering most of the foundational aspects that we still look at today in modern college or higher level education courses.